Hi, to continue the post-processing that we were doing, previously we ran the simulation from 0 to 60 and we have the signal. So if you look at that coefficient, direct coefficient in this case, you will have the idea that kind of is reaching a periodic behavior. But remember, you have different signals, so you have to look at all the signals, all the information you have. So as you look at the lift coefficient signal, let me go here and let me apply plot. So we have the plot. So I run up to 300 seconds, but previously it was up to 60. So let me plot it here. And see that by looking at the second one, we see here that we have another frequency within our frequency, another harmonic. So maybe we cannot say here that this is statistically steady. We see another frequency, so it might be a better idea to run for a longer time and see if this frequency disappear, or if you keep, or if that frequency stays there. We need to apply some other time series post-processing technique just to remove that other frequency. Okay, so if I plot, for instance, up to 100 here, see that kind of is damp here. At the beginning we have a strong oscillation, but then it's still kind of we have that frequency there. But if we keep running, see that probably here it's becoming better. Okay, so see that probably here is better, but here the idea is that be careful when running, when you are doing the sampling. Just don't look only at one signal, look at all signals that you have, leave direct coefficient, put many sampling plots, sampling the solution there, and see what is going on. Okay, sometimes it can be really misleading. We're using this case that probably this is not a normal case. Now as you're doing airfalls, you won't have this strong shedding, this strong dependence, but kind of as you're working with cylinders where you have this shedding, it's a good idea to sample in a lot of things just to get that shedding frequency. It still opens the problem why the frequency of one signal is the double of the other one, so that you should answer that. And let's do a little bit more post-processing here. So see here that it's giving us all the descriptive statistics. Okay, so here you have minimum, maximum values, mean value. Okay, so see that it's close to 0, and the variance. Remember, the variance will give you kind of how far are the values from your mean, but as you take the square root of that one, you get the standard deviation. That is more interesting for us. So this standard deviation will give you the dispersion of data. Okay, and remember that standard deviation can be larger than your mean value. So for instance, in this case, if we take standard deviation, will be the square root will be 0.9. Okay, see that your mean value is 0, so, and even your maximum, so you have strong peaks, and it may happen. Okay, but sometimes you get standard deviation much larger than your mean value, or even your minimums and maximum that you have. It is those can be outliers, so you will careful. You should be careful, but that doesn't mean that it's wrong. Okay, but analyze your data. So we can go here also subtract mean value. So if you subtract the mean, see that we're getting 0, and this is what is called the root mean square. Okay. So now we have the root mean square that for us is more interest when working with turbulence, because we use this value, we have different stream, we can compute the turbulence intensity. Okay, and you can do the same with the other signals. So as we go to the direct coefficient, so let me load direct coefficient. Okay, so see that we have a long signal, we have here a long transient. So definitely here, see that we need to erase from our transients some information. This one is no good, and also probably up to 50 is no good. You should erase that one, then do your statistical post-processing starting from that. Okay, and as we go, for instance, up to 200. Okay, see that we have kind of a periodic behavior, but let's remove the first 100 seconds, and we can do our statistical post-processing here, the descriptive statistics, and you have here your mean value, minimum and maximum. By the way, also we just set up this case, Reynolds 10,000. We put values. The mesh probably is not the most beautiful mesh, the best mesh, but it's just to run. So these values may not correspond to experimental ones. Okay, I think they are close. The experiment there is a curve for this one that it should be around that one, but maybe probably as you compare might not correspond 100%. Okay, but it's not a problem. This is just a test. Against you, the variance, see that will give you how far are these values from the mean values. Okay, and then you take the standard deviation of this one, the square root of the variance, you get the standard deviation that in this case should be something about 0.15. Okay, so it's giving you the dispersion about this, and that dispersion is telling you is you get one standard deviation is like, if we recall, 68% of your values are contained. Within that, if you take 2 times the standard deviation, you will have I think 95% of your values contained within those range. Okay, that kind of will be a confidence interval. And here you can see clearly that if you have, for instance, this one here can be an outlier. It's something close to 1.6. It's very, very far from the mean plus the standard deviation. Okay, but can happen. Okay, it's not a problem if you have standard deviations larger than your mean value. And remember, just subtract your mean, you will get the root mean square. Okay, that's more interesting, but it's simply you are doing all this statistical analysis about 0. Okay, so subtract the mean and you get everything about 0. And okay, so now I also have a lot of information just to do nice plotting. A lot of people like to do this plotting, so I'm using tutorial and other software. So doing more advanced stuff probably is a little bit difficult in Fluent. So see here, for instance, I put a few lines. So I will do sampling here. I will see, for instance, velocities here, vorticity, whatever, and see that I also have these lines here, normal to my surface, where I can do the sampling to plot the boundary layer, the dissipation rate, projection of turbulent kinetic energy. Okay, you can do all the sampling there. Okay, so this is more flexible. So just to show you this animation here, so I compute many fields. Okay, so let's see, this is a velocity field. Okay, so let me press play and let's see what's happening. So as you see, you have an initial transient, it seems to be steady, and then you will have the onset of the instability. Okay, so now kind of the wake have been developed, and see that is doing kind of a switching, is going down. So this is everything that we're seeing, the lift signal. See that you have the wake going down, you see that reflected in your lift signal, but now see that it's now doing another switching, is going up, and precisely that everything you're seeing that in your lift signal. It's going out, and it will oscillate a little bit. So see that 50-60 seconds this wake it is oscillating. I will let it run, but will oscillate up to 300, but there will be one point that after top seconds it will get more stable. Okay, so keep oscillating, see that it's getting better here, but still you see that switching. Okay, which something that you won't see is you run the K omega SST or any of the viscosity models, or the standard ones, you won't see this switching. It's difficult, but the less that is resolving everything, it's not adding any modeling here, we can capture that switching and those turbulence structures that probably are causing everything, generating that switching between the interaction, because here you have many vortices and you have a strong interaction. You see that even 120, 30, still there is some switching. Okay, so there is a release frequency of these vortices, and then they interact between each other, and then cause this wake to switch with a given frequency that can be calculated using the time series and specific signal processing. Okay, so it's still running. Very nice. And the idea also when we were talking in lecture 2 or 3 that I show you one plot about the turbulence spectrum. Remember that you are going to put here many probes all around where you have the fluctuations, and then there you will save that information, and then you can use that information to compute your energy spectrum. But many more things you can compute using that information. You can see how this data is correlated. So see that here you have vortices. As you put many probes, you can see that vortex can correlate in a given distance, and you can get the length scale. But in any case, you can see that visually here. But usually that kind of method is used more for you have experimental data, okay, which is difficult. But if you're doing CFD, you just can't just plot everything, and you can measure your turbulence scales there. So let me stop here and show you that. For instance, I have also the field, the vorticity field. So it's the normal to the plane XY. Okay, so I have it here. And this one will give you also rotation. So see that red will be rotating counterclockwise, blue clockwise. And let me play a little bit here and see here that you have all the vertical structures. Again, it's the idea that you put what I was telling you here directly, you can measure the dimension of your largest scales. And as we were telling that usually largest scales are about the size of this obstacle that you have here, okay? So see that they are about that one. Probably you might have the impression that it's larger, but remember that it's rotating, it's swirling. Okay, so the idea is putting some probes to measure the distance is that you can go put a probe here, another here, here, and you see when this data decorrelate means that you are outside that vortex, and now you can get the dimension. So we're going to see that one in the statistical part. I don't do it very often in CFD because you can get it directly from here. Okay, so let me play here and see here nicely all your vertical structures. So in 2D, usually we use vorticity to visualize the vertical structures, and we go to 3D, there are some other criteria. Okay, you can use also vorticity, but there is like lambda 2 Q criterion that are much better. The advantage of vorticity is that will give you rotation. In what sense is rotation? The other criteria will capture very well those structures, but it's not telling you much about rotation. But you can find also, you can detect those vortices using pressure as well. So we have pressure field. Remember, a vortex is an area where you have a low pressure region. So if I plot here, P, see that we have all the vortices there. We can also plot X component, Y component. Okay, here I have more information. So you can save a lot of information. So let me show you. For instance, now I will plot the velocity magnitude in this line there, so just to see the wake. And if okay, also I computed the mini statistics, so let me show you. This is interesting. So look at that, to know also where you can start, or from where you can start to do your sampling. It also is a good idea to save this information and visualize. So see that you start a simulation. So this is the mean quantity. So this is computing all of your on steady statistics is computing time averaging everything. So you see that at the beginning the solution still is not average. It's not statistically steady. It's still evolving. Okay, so remember we're looking mean quantities here. It's not instantaneous values. So the idea is when you see that this quantity is not changing anymore, you can say, okay, from that point I will start to do my sampling because I know that I have good statistics. Okay, see that kind of it is stabilizing here, downward, it's changing, but we know that this will also do some switching, okay, and will go all and will affect my statistics. So see that I cannot say that 50 or 60 is a good interval to start my sampling. Okay, so we let it run, and let me stop and go a little bit faster here. So see that net goal 90, see that we see that it's switching, and kind of already here, I think in 150, kind of is stabilizing straight. So now this is a point that we can say that all this statistic that we took, like CLCD values at the probes, probably starting from 150, are more reliable. This statistic will change a little bit. You see that here where it's still accumulating values, but we don't see anymore the switching. Okay, so this is interesting. That's what I say, always in steady computations, compute on a steady statistic. Again, I want to stress this one, that this is a small case, and usually you don't do all this post-processing, but as it's the smallest case, it's interesting to put all this here because we can do things fast. Okay, but simple cases is usually you don't go and do this elaborated post-processing. And okay, let me click here. What else we can access? So you have all your turbulence quantities. Remember, we'll continue here about turbulence intensity. So remember that the turbulence intensity is a ratio between the root mean square of the velocity divided the free stream. So see here that these are the areas where you have your turbulent model is kicking in. You have the intensity. Okay. Then you have the kinetic energy, the production of K, everything there that you can use to post-process. So what I wanted to do now, it was to plot the velocity at the wake. Okay, so we have this line here, and we can create also monitors there. So in the instant, I already create this one. I have this one, so I put it there. That is by plus. It's this one. Okay. So basically now I'm just plotting all the information that is passing there, and we can see what is happening in the wake. Okay, so you see that we have here momentum deficit, momentum fade. Okay, and this is a time series and dependent data, and see how it is evolving. So here you will see how the vortices is passing. Again, from this information you can also get an idea of dimension of those vortices, the large structures, and even if your mesh is very fine, also you can get an idea of the fine structures. Okay, so everything that is passing in this line you can plot it. So I have different lines that I put there. So let me put this one here, that horizontal one. So again, we can do that plotting there. So let's see that in that one I'm plotting the two components of velocity. Okay, and see that this data, as you go and do a formal analysis, see that this data is correlated, and using those correlations you can get many more information. Okay, let me start here. Also, for instance, I have the y plus value on the cylinder surface. Okay, hide this one. No, I don't want that one. I want this one. And as I told you, that it's impossible to have a constant y plus. It's changing because it depends on what shares stresses separation. But see that here you can plot it, and this is a quite good mesh. Okay, but probably it's not a perfect one. So you are going to go wall resolver, that should be as close as possible as one. But see that everything is below 3. Okay, and we can plot also stop the mesh. Okay, so look at our mesh. So probably will be better to add more inflation layers. Okay, so here I think we have 8, but probably more will be better, and make it finer close to the surface to be closer to 1. Okay, and then as we look at the wake, so let me look at the vortices here. So later also there is another very nice criterion to see if we're resolving well the mesh is resolving well all the scales. But see here that we were talking, there was one slide that we were talking to resolve a vortex, probably the minimum, the larger scale, the absolute minimum of cells that you need to put is about 5. And see that kind of here we have 5 cells. So all the large one, you need a minimum of 5. Smaller, okay, smallest vortices you need like 2 to resolve those one, but larger scales we have those, say that 5. So this mesh is okay in the far field. Okay, to resolve large scale, but it's also remember that you might have also some small scales here. This mesh is not resolving those there, but it's interesting. Let me play here and see. Okay. So see that here this comes in on a small scale, and this mesh probably is the bare minimum to resolve it, but probably would be a good idea to have a finer, even finer mesh closer to this one in order to better resolve those vortices closer there. Okay. So it's very powerful. It's not also the colors that people like, but these colors also you have to be very critical what you are doing in the colors. And let me see what else we can plot here. What's this sampling? So we have the Y plus. Then also put one for the vorticity. Okay, so this vorticity is being sampling. Okay, sample in this horizontal line, and see that here you can see the vortices also. So kind of you come here and you see that the change in sign is here. So this vortex is about 1 meter. Okay, and here also you can get the dimensions just by looking at that data. What else can I plot? Can go here, velocity, magnitude. Okay. This one. So here we have in our horizontal line, this line here, I'm plotting some velocity profile. So see that the blue one, the cyan one, is your velocity profile, and then the green one is the dissipation. Okay, but it's better, probably it's better to use this one. Okay, I have 3. So here I have velocity, dissipation, and production. So remember that this is what is called the budget, turbulence budget. So you have production and dissipation, or destruction. Okay, some books and some reference they call it destruction, dissipation, and then production. So remember that we're in equilibrium, so they are kind of similar. So then as you go and take this integral of everything, you will see that they are kind of very similar. Okay, but remember that the maximum production, it is in the buffer layer, and then also dissipation goes to the viscous layer. Okay, so basically you see that one velocity profile. Probably we can also do the plot and see instead of putting this and the normalize the Y plus, but I'm quite sure that the production here, okay, maximum, see that it peaks here, and this area is likely probably will correspond to, all this area will correspond to the buffer layer Y plus more than 10, and then dissipation will go to the viscous area, to the viscous layer, and see we can play, and you can see how these structures are changing in time. So remember always, these are very interesting plots, okay, but again, in industrial cases, okay, you follow good practice and you know that you will get good results. This can be very expensive. Okay, see that we're basically sampling this line, also needs to be always normal to this one. So here you can sample in your work share stresses and then normalize everything. In my case, I'm not normalizing anything, I have physical units. But look at my velocity profile passing there, so let me put their velocity instead. Okay, so see that the boundary layer, okay, which is the cyan line that you see there, and then we can also plot the total kinetic energy. So remember that you have a resolve field, and then you have also what is model. Let me plot the total kinetic energy. Let me change my scales. Okay, instead the resolve, let me see what we have in the resolve one, which. Okay, so see that the resolve kinetic energy. So see that maybe here I see that by definition should be 0, but see that the Turbulence model is also, this is a wall modeling less, and it's put in here is modeling the turbulent kinetic energy. Well, no, this is resolve a spectrum, but also should have this grid SGS kinetic energy. And let's see if this one is kicking in. Again, see. So this corresponds to the model part. And see that my turbulence model is put in there. Okay. So all this area here is kicking in, and then here this stagnation point, this part is laminar. See that we don't have fluctuations there. Okay, so this is the grid scale, the modeling part, and then we have also the resolve part. The same idea. You go close, see that it's 0. You don't have any fluctuations there, and then you start to grow the perturbation. Again, here I am putting values. This not necessarily means that this is correspond to your boundary layer or where you have the turbulence. Okay, you need to find those regions. 0.5. Let me put it 0. No, larger. I need to put it 0.5. Okay. So see, closer to 0, then you start to have fluctuations here. See that separation, there are no fluctuations, and goes back here. Again, also we have dissipation, that you have it. In this case, dissipation is model, okay? So we should compare, we have dissipation rate, okay? And here we can say probably, where you have dissipation is where all these turbulence is dissipated or destroyed. So remember, you have dissipation, production, then in this bucket you have many terms. You will have diffusion, okay, it's another correlations like velocity, pressure correlations. But the most important ones is this one, destruction and production. Okay, and I think that's all that I wanted to show you about this one. So as you have time, just you can run a little bit longer this signal, and you can do the post-processing of this one. It's relatively fast, okay? So, okay, see you next time, bye.